Okay, so thanks Cindy and Joseph and the team here at Northwestern for organizing this wonderful event. So I'm Josué Baggio. I'm based at NTNU in Trondheim, and today I'm going to tell you a little bit about our research on composition and compositionality in a parallel architecture for language processing. So I think we can all agree that the goal in language processing is to compute meaning. So the goal is understanding. And it is to do so from given physical stimuli, whether it's sound waves or light waves or something else. And I think we can also all agree on that there are different sources of information that can be harnessed in this process, and that syntax is just one of them. So the question that we want to ask and maybe try to answer at this workshop is, what is the role of syntactic information in this very complex process of meaning construction? Now, the standard answer in formal semantics and areas of philosophy of language is the idea of compositionality. So I'm sure many of you are familiar with this idea, but that's the idea essentially that complex meanings, so meanings at the phrase and sentence, maybe also the discourse level, are computed as a strict function of the meanings of constituents and syntactic structure, and nothing else. So I think this leads naturally to what we might call an architectural hypothesis. So the idea that in the mind and in the brain, there is an exclusively syntactic and lexical route to sentence level meaning. And that's kind of a definition which is due to philosopher Emma Borg, which I find quite effective in this context. Now, of course, as we know, there are challenges to compositionality, so both formal challenges and empirical challenges. And empirically, the fact is that competent speakers of a language can actually assign multiple meanings to expressions in that language. And some of those meanings may or may not be compositional. And I find this just a very deep and fascinating fact about human language that still awaits explanation. So, of course, idioms are a classic case. Like if you say he is really on the ropes now, you may mean this in the idiomatic meaning, that someone is in a difficult situation, or literally, if you're talking about a boxer, he's literally on the ropes. But there's many more examples. For example, ordinal adjectives, like the first person landed on the moon in 1969. So this doesn't mean what the compositional analysis would suggest, that the first person ever landed on the moon in 1969. It means that the first person who landed on the moon did so in 1969. And that's very difficult to get using standard compositional analysis. Right? So similar example, the first case of AIDS was reported in 1975. It doesn't mean the first ever case of AIDS. It means that the first reported case of AIDS was reported in 1975. So Pelletier in a paper in Topo has many other nice examples of how compositionality can fail to give the meanings that are appropriate or what appear to be the intended meanings. So this leads me to a second architectural hypothesis, which is the idea that I'm really interested in and that I want to put on the table for this workshop, namely that there are not one but actually two routes to phrase and sentence level meaning, only one of which is strictly syntax based and obeys compositionality, and the other doesn't. So what do I mean by this? I'm going to sketch a general idea of a parallel processing architecture where something like this idea can be concretized and made explicit and testable. So this is the model that I'm currently working on. So we have inputs, which may be morphemes or words, which activate these L lexical representations, which may be bits of phonology, syntax, semantics. If you think of Jack and Duff's models, that's the idea. And the goal, as I said at the beginning, is to compute an interpretation or a model. So in the sense of classical formal semantics, that would be a reference structure that satisfies your input string. Now, what is special about this model is that in order to map lexical representations of morphemes and words onto a discourse model, incrementally, step by step, you need to go through two intermediate representations, which is the S and R representations here. So the R is essentially a relational structure. So it's a description of a set of semantic dependencies, what people in NLP call a semantic parse. And the S representation is a structural analysis, a standard syntactic parse, for example, in terms of syntactic dependencies. So we take lexical information, we project that onto a discourse model, and we do so through two parallel intermediate representations: a semantic representation, a set of semantic dependencies, and the syntactic representation, a set of syntactic dependencies. Now, naturally, we have two streams in this model, what I will call a grammar stream or G stream, which is effectively lifting morphological and syntactic information out of the lexical structures and using those to build the structural descriptions, so the syntactic parses. And then through bottom-up syntax-driven composition, as regimented by the principle of compositionality, it's making its contribution to the discourse model. And then we have the second stream, which is the meaning stream, or what I would call the M stream, which is lifting bits of semantic and pragmatic information out of the lexical representations. It's using those to compute semantic relations, a semantic parse, and in turn using those in interpretation to contribute to the discourse model. Now, as I said, there is parallelism in the model in the sense that for each morpheme or word, which is processed incrementally, both streams are active at the same time. However, there is dynamic balance. So the balance between the two streams may change from one word to the next, and depending on a number of factors. So one stream may take the lead over the other. For example, the grammar stream will take the lead in when we are processing function words, and Yosef's talk is a very good example. Negation is a classic case. Quantifiers also, and other closed class words, or when the syntactic complexity of the strings exceeds certain boundaries. So then you're relying more on the grammar stream. In contrast, the M stream, the meaning stream, is more prominent when we process content or open class words, like nouns, verbs, adjectives, and so on. And also when rich contextual information is available. So the first talk this morning, I think, highlighted very nicely this fact that rich contextual information is very often available when we understand language, and this is harnessed specifically by the M stream in our model. So there's parallelism, there's a certain division of labor, and the dynamic change in balance from one bit of information, from one word or morpheme to the next, between the two streams. Now, there is also, I would argue, a way of mapping classic language-related ERP components to each of the four phases in this parallel architecture. I'm not going to talk about the N400, sustained anterior negativities, and the LAN effects because I don't have time to do that, but I'm going to focus on the P600 as a marker of essentially processing costs in the bidirectional mapping between the model, the interpretation, and the structural analysis. And that's where composition and compositionality come into play. So I'm going to talk specifically about the mapping between the structural description and the model, which is classically informal semantics bottom-up composition governed by compositionality. And second, the inverse mapping, which I will call top-down prediction. And I'm going to explain in a minute what I mean by prediction in this context. So the mapping between the model and the syntactic analysis. So I'm going to present two studies, a computational study, which is effectively a MAR level 2. So it's an algorithmic model of existing ERP data, looking specifically at ERP effects of top-down prediction. And second, an EEG study, which we just finished in our lab, looking at the effects of bottom-up composition. So the first route, meaning to structure, so the top-down prediction idea. If there has to be mapping of meaning to form, we need an autonomous semantics. So Jackendorf has written a lot about this idea of an autonomous semantics, the idea that meaning can be constructed ignoring or overriding syntactic information. Moreover, according to this idea of autonomous semantics, semantics may affect how grammatical structure is processed. So going against the traditional syntax proposes, semantics disposes view of generative grammar and formal semantics. So an influential ERP study, which was published 15 years ago by Albert Kim and Lee Osterhout, very elegant and very powerful study, shows exactly this. So they used ERP sentences like the hearty meal was devoured by the kids and the hearty meal was devouring the kids. I'm sure many of you have seen these examples in the data. Now, the key idea here is that both sentences are grammatically well formed. So if you run a parser on these two sentences, the parser will give you the correct syntactic analysis. However, there's something odd going on with two, namely that the arguments don't quite fit thematically with the verb. So devouring should therefore be processed as a semantic anomaly. So people should detect that there's a semantic incongruity here. However, instead of the expected and for-ended effect, Kim and Osterhout found a P600 effect. So both when they compare their so-called attraction violations, so the hearty meal was devouring at the verb, to a passive control sentence, the hearty meal was devoured. And when they compare the same sentence, the hearty meal was devouring, to an active control sentence, the hungry boys were devouring. So you see very clearly, no N400, but very clear P600 effect. So following in time the N400 and with a different polarity too. So what's going on here? How do people process sentences like the hearty meal was devouring the kids? Well, there's two options, also in the parallel picture that I've just sketched, but in general, there's two options. Either syntax takes the lead in processing, so has priority, and then the system should parse a sentence like two very easily. But in that case, it should detect a semantic anomaly, so a mismatch between the thematic assignment between the verb and its arguments. So an N400 should be found. If instead semantics had priority, the system might be able to interpret two easily. So it might, for example, assign thematic roles based on stored statistical relationship, so knowledge of what is most plausible, more likely. But the question is whether that interpretation would be consistent with a bottom-up syntactic parse of the sentence. And the answer is that it probably won't, right? So the semantics here would assign the following thematic and grammatical roles to the verb's arguments. So the hearty meal would be a plausible theme, and therefore, by some linking hypothesis, a plausible grammatical object. Whereas the kids would be a plausible agent, given the verb, and therefore a plausible grammatical subject. That's what your semantic system, or what your M stream, would come up with in this case. Now, a syntactic analysis tells you that this is not right. So the hearty meal in this case is the subject, and therefore probably the agent, and the kids is the object, and therefore probably the theme. So there's an inconsistency, there's a mismatch between the way a semantic processor could assign thematic and grammatical roles to this sentence and the way a parser does. So semantic relations between content words suggest a plausible interpretation of this sentence, which is, however, incompatible with the syntactic analysis. And it's precisely detection of this inconsistency between the most plausible, attractive interpretation and the actual bottom-up parse of the string, which gives rise to the P600. Okay, so how can we model this so that we can make some algorithmic sense of the process? So I think we need an idea along the lines of prediction in this case. So we can view the two systems, so the two streams. I call it A and B here, so it's meaning and grammar, respectively, as producing the same outputs, say assigning grammatical labels to the verb's arguments. And the idea is that one system may run ahead of the other. So it may produce the output before the other does, or it may make that the same output available earlier to, say, central systems. So in our model, so that's our first implementation of the parallel architecture, we have a meaning stream, which is essentially a deep neural net at heart, and our grammar stream, which is the Stanford Core dependency parser. They work in parallel, and the task for both is to label the arguments of verbs. So to say which is the subject and which is the object. They do that in parallel, but the meaning stream is allowed to present its output to central systems, so to this additional error detection system, earlier than the syntactic parser does. So here's some of the analysis that they produce. I'm just going to go through the attraction violations. So the bubble gum had been chewing by the boy, which shows on the bottom the output of the meaning stream. So you have this arc, which essentially tells you that the semantic system thinks that the bubble gum is a plausible object for chewing. And on the top, you have the dependency arcs that are produced by the syntactic parser, which in this case obviously tells you that the bubble gum is the subject of this sentence. So there's a mismatch between the semantic parser and the syntactic parser in terms of how they label the arguments of the verbs. And I'm going to argue that this is precisely what is reflected in the P600. So if we run our model on sentences from the Kim and Osterod corpus, so we are treating a set of experimental stimuli as a little NLP corpus, we get very good accuracy, 84% with the deep neural net for classifying attraction violation sentences. So the model is pretty good at detecting when there is an inconsistency between the way the semantic system and the syntactic system assign grammatical roles to the verb's arguments. So that's, I think, at least the first proof of concept that ideas along these lines, a parallel architecture with parallel systems that can produce the same outputs and where those outputs are then compared, can go some way to capturing existing experimental data. So what about the inverse mapping? So the more traditional mapping of structure to meaning, the other way around. So the prediction here would be, again, that we find P600 effects in such cases. So the parallel architecture specifically predicts similar neural responses. So, for example, the P600 in ERP data. There's, of course, much more in the brain, but we focus on ERP data in this case. For predictions, so the mapping of meaning to structure, and composition, the mapping of structure to meaning. So in both cases, bidirectional mapping costs should be reflected in larger P600 amplitudes. So how can we study composition? Specifically, how can we make sure that the meaning stream is shut off as much as possible so that lexical and syntactic information alone can be used in the process of deriving meaning? Well, the first idea is obviously to minimize context. So use, for example, phrases, noun phrases, instead of whole sentences or discourses or lists. And the second idea is that one should also try to minimize the role of stored knowledge, or semantic relations between content words. So there's a very successful line of work, which I'm sure most of you are familiar with, from Lena Pilkanen's lab at NYU. And I think her lab is represented here in the poster section, so I'm looking forward to that as well. And we build on that. So we wanted to do an EEG study using a similar experimental design where we look for the ERP signatures of bottom-up semantic composition. So here's our design. Sorry for the Norwegians, so there are glosses in English. What we wanted to do was essentially to compare 4 semantic conditions: a real president, a current president, a fake president, a former president, to what we call non-semantic conditions. So conditions where the adjective is replaced either by a non-word or by a pseudo-word. So then we have 2 different ways of manipulating the adjective. So we either look at the intensional properties of the adjective. So we want to have temporal and modal adjectives, like real and fake would be modal adjectives, and current and former would be temporal adjectives. As well as we want to manipulate the contribution that they make to the denotation of the noun phrase, whether it's privative or non-privative. For example, a fake president is not a president, so that's the privative interpretation, and a former president is not a president now, so that's the privative temporal interpretation. So what we want to have is a set of conditions where we can compare the 4 semantic sentence types to the 2 non-semantic types. So looking at the signatures of composition, semantic minus non-semantic conditions. We want to look at the effects of denotation, where we compare the privative to the non-privative trials. And finally, at the effects of intentionality, where we compare the modal to the temporal. So we had independent reasons for looking at denotation and intentionality here. There's a huge literature in linguistics and psycholinguistics looking at these kinds of adjectives. But the idea here is that we want to make sure that the signature of composition, so the effect that we get out of the contrast between the 4 semantic and the 2 non-semantic conditions, is actually different and not driven by the effects of denotation and intentionality, because it should be independent of those. And here's our main results. So looking at the comparison of the 4 semantic conditions minus the 2 non-semantic conditions, we see a very clear P600 effect, which you see there after the unfounded peak. So here's another channel, and here's a statistical representation of the effect. So that's a cluster-based randomization algorithm. And here's the topography, so classical centroparietal topography for the P600 effect. So a very clear effect in this case. So summarizing the results, we get a P600 effect for composition. We get an N400 effect for intentionality, again at the noun, so comparing the temporal versus the modal adjectives. And we get a negative post-N400 effect for denotation, which is very consistent with the SAN literature and referential ambiguities and so on, following the N400 for the comparison between privative and non-privative trials, again at the noun. Now we have just replicated in the second experiment our main P600 result of composition using different adjective types and using a different manipulation than crossing intentionality and denotation. So some conclusions. I wanted to give a role to this classic concept from philosophy of language and formal semantics, which is compositionality, within an architecture of language processing that looks plausible, both psychologically and biologically. And I have tried to argue that compositionality is worth maintaining, so it's a key and important concept for modeling syntax-semantics relations. However, I've also argued that it plays a very specific, very limited role in the cognitive architecture of language. So I've argued that interpretations are computed through interactions between 2 parallel processing streams, a meaning stream, which is sensitive to context and to stored semantic relations between content words, and the grammar stream or G stream, which is instead producing parsers, largely based on information provided by function or closed class words. And I've also argued that compositionality, perhaps a bit surprisingly, if you think of it as a principle that constrains meaning, does not apply to the M stream, but it actually applies to phase 2 of processing in the G stream. So the mapping between the structural bottom-up parse and interpretation, as in classical formal semantic theories. So it's effectively a constraint on bidirectional mappings between structure and meaning. And I've also argued and showed computational and experimental data to the effect that bidirectional mapping costs, constrained by compositionality, are reflected in modulations of the P600 amplitude in ERPs. So we know that from a huge literature on P600 effects in syntax, from the Kim and Osterhout kind of work, which has been followed up by many other studies along the same lines, as well as by our own 1 and now 2 ERP studies trying to do something like Lena Pilkanen's lab has done, but with ERPs and producing, again, P600 effects. So what's next? The next step is, of course, to go from architectures and algorithms, so MAR level 2, down to MAR level 3, and start thinking hard about what could be the neural mechanisms that implement such an architecture. So I just want to mention a few friends and collaborators. So Peter Hagort and Michiel van Balgen, who were my former PhD advisors and got me into thinking about compositionality in the context of language processing. I want to mention my own book, which appeared last year for MIT Press, where I describe in some detail how the meaning stream works, work using NLP techniques, which is the model that I presented with Olivier Michelon, which has appeared this year in Neuropsychologia, and the new EEG work with our postdoc, Isabella Fritz. So for those of you interested in meaning composition and specifically mechanistic models, Andrea Martin and I have a theme issue for the philosophical transactions, which should be coming out early next year with a bunch of very, very nice contributions specifically on this topic. And thanks so much for your attention.